Myself, Dr. C.R. Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the theoretical analysis for Judd Ofelt intensity parameters. This we are going to study from the absorption spectra. This is one of the important topic from the laser glass spectroscopy. So last one previous session was discussed on the optical and nonlinear properties of chromium tetrastope, yttrium, aluminum, garnet crystal. In that we are discussing introduction, theoretical basis on jet scan technique and optical properties conversion. In this jet scan technique, we have studied the nonlinear properties of the nonlinear refractive index and the polarization difference of the absorption of the glass material. Thin samples we have studied in the last section. So present topic is the theoretical analysis for Judd Ofelt intensity parameters. The outline of the today talk is on the optical absorption spectrum. So in the optical absorption spectra, we are taking one example of the erbium 3+ dope, BSGD calcium erbium 0.5 gas. So we need absorption spectra of the any one of the erbium dope, rare earth dope glass sample. So that is we are taking example of the erbium 3+ dope, 0.5 concentration of the glass. Next, we are going to calculate the oscillator strength. Oscillator strength is effective experimental oscillator strength and calculated oscillator strength. We are going to calculate both experimental as well as calculated by using the Judd Ofelt intensity parameters. Third one is the root mean square deviation. That means RMS deviation. We are going to study by using the F experimental and F calculated values. Next, Judd Ofelt intensity parameters is importantly three parameters, that is omega 2, omega 4 and omega 6. These are the, we can say, is the intensity parameters or Judd Ofelt intensity. This is Judd and Ofelt, both scientists were derived the theoretical model for the to study the intensity parameters of the by using the erbium doped absorption spectra. From absorption spectra data only we are going to calculate in the Judd Ofelt intensity parameters of the omega 2, omega 4 and omega 6 values. Finally, we are going to discuss about the radiative properties such as radiative probability, radiative lifetime, branching ratios BR and stimulated emission cross section. These four important parameters comes from the radiative properties. These are we are going to study by using the Judd Ofelt intensity parameters. For example, we are here taking the erbium 3+ dope, BSGD calcium erbium 0.5 glass sample. Next, optical absorption spectra of this is the example of the erbium doped silicoborate glasses. This concentration of the erbium is 0.5 glass. So in this glass, we are getting the absorption spectra. By using absorption spectra only, we are calculating the JO parameter, that is intensity parameters. So in this erbium 3+ and this ground state is quartile 15/2. From ground state to quartile 15/2, different excited state we are observing. See here, different excited transition we are observing. One is a quartile 13/2 is the higher wavelength, and quartile 11/2 and around higher wavelength and near infrared region. Remaining are the UV visible region, we are getting a few important peaks that is related to the erbium 3+ ion. From ground state, quartile 15/2, different excited state. So among the year 1, 2, 3, 4, 5, 6, 7, 8 peaks we are observing. In the among the 8 peaks we are getting the among the 9 absorption peaks we are observed in this absorption spectra, but in a well resolved absorption spectra is 6 one. So 6 absorption transitions are well resolved to the calculate the oscillator strength of their energies. So by using this 9 absorption peaks, these are the very small peaks, but we are unable to calculate the absorption under the area under the absorption curve. That is why you are selecting the well resolved absorption peaks of the 6 absorption lines we are taking to the calculated the Judd Ofelt intensity parameters. Before going to calculate the Judd Ofelt intensity parameters, we need to calculate the oscillator strengths by using the energy levels. So each and every transition having the correspondence energy level, that energy delta E value corresponding transition, that we are calculating the oscillator strength by using the formula is there. So this is the oscillator strength calculation. The intensity of an absorption band is generally expressed in terms of oscillator strength. The experimental oscillator strength, F experimental of FF transition. So each and every F black elements, this is transition from the F to F transition only. The absorption spectrum can be obtained by the following expressions. So this expressions comes from the F experimental value. That is F experimental formula is 4.318 in 10⁻⁻9 integral of summation mu dV. The summation mu v is the molar observability of the wave number. So corresponding wave number we are calculating the molar observability by using the observation spectra. By using this observation spectra, each and every observation peak, we are calculating the molar observability. That is comes from the epsilon mu dV. So in this formula, here we are calculating the each and every observation peak area, that thickness and concentration we are calculating by using the, here we need thickness of the sample and concentration of the sample. That's here we are using erbium concentration 0.5 mole concentration. In particularly erbium 3 plus ion, thickness we required, concentration required. See, both we are using to calculate the, and also we need to calculate the area under the absorption curve. Each and every absorption, okay, we have to calculate the area, this complete area and this area by using the graph sheet, or we can use origin. We can use in origin and using Excel sheet, we can calculate the each and every absorption peak area under the absorption peak. By calculating the each and every absorption peak area, and we have to multiple with thickness and concentration, and we are getting the molar observability at a particular wave number or energy. In which absorption peak having the that energy wave number, that corresponding value you are getting, that value you are multiple with 4.318 in 10 power minus 9, we are getting the FX meter value. So the theoretical oscillator strength of the FF transition can be evaluated by using the Judd Ofelt intensity theory. So by using the Judd Ofelt intensity parameters, we have to need to calculate the first FX meter value. By using the FX meter value, by substituting the Judd Ofelt intensity theory, we can get the F calculated value. This is experimental value, other one is a calculated value. We are observing by using the Judd Ofelt intensity theory. See, this is the oscillator strength of the F calculated and the JO parameters. So in this theory, the calculated oscillator strength for an induced electric dipole transition from the ground state to an excited state is given by. So each and every absorption peak starts from the ground state to excited state. So if erbium 3 plus ions energy levels is 4 tri 15 by 2 is the ground state, different excited state, we are getting different excited state of the erbium 3 plus. So each and every excited state, we are going to calculate the F calculated value. So in that, in erbium 3 plus ions, we are getting totally observation 9 observation peaks we are observed, but well resolved observation peaks are only 6 only. By using 6 observation peaks, we are going to calculate in the Judd Ofelt intensity parameters by using the formula of F calculated value. So here F calculated is 8 pi square mc mu n square plus 2 whole square divided by 3h into 2j plus 1 into 9n, summation of lambda equal to 2, 4, 6. So sigma lambda equal to psi j mu lambda into psi dash j dash. That means ground state to excited state of whole square. So by using this formula, we are going to calculate. Here n is the refractive index of the sample. So by calculating the F calculated value, you need refractive index of the glass samples. So erbium 3 plus ion refractive index we need to get. So that value we are substituting by using this formula. Next, J is the total angular moment of the ground state. That is, this is quarter by 15 by 2 is the, this is the J value we have to substitute by using the quarter by 15 by 2 of the ground state of the erbium 3 plus ion. Next, mu is the energy of the transition. Each and every absorption peak having the energy, that energy we have to substitute. So lambda is, say lambda equal to 2, 4, 6. That is intensity parameters is 3 is the intensity parameters of the Judd Ofelt intensity parameters, that is omega 2, omega 4 and omega 6, that we are calculating by using this formula. Next, unit matrix, that is mu square is the doubly squared reduced matrix. This reduced matrix elements we are kernel paper, we need to, by using the refer this paper, this is reference number 5, we use that paper, we need to get the reduced matrix elements of the each and every erbium 3 plus n and particular transition. So among the each and every transition having the particularly wavelength, that corresponding wavelength we need to take the reduced matrix elements, that is U square values, U square, U4 and U6 values you need to take for each and every particular excited state energy levels. That you have to substitute in the formula, then only we are getting the Judd Ofelt intensity parameters. That is the rank of the lambda is equal to 2, 4, 6, which are calculated from the intermediate coupling approximation for the transition from ground state to excited state, psi j to psi dash j dash. This is ground state to excited state. So this is the, we need to calculate the, by using the oscillator strength values. So by using the oscillator strength values, you need to calculate the approximation values of the ground state to excited state. So this formula, this n we know, refractive index, J is the total angular momentum, and mu is the each and particular absorption peak energy value, that is transition in centimeter inverse. Next, rank of the lambda values 2, 4, 6. These are the Judd Ofelt intensity. By using this formula, we are calculating the F calculated. In the previous formula, we are calculating the F experimental value. So F experimental and F calculated value, we are calculating by using these two formulas. Then by using these two formulas, we are getting oscillator strengths of the F experimental and F calculated. By using these two values, we need to calculate the omega parameters, that is omega 2, omega 4, omega 6 values. Next here, we need to calculate the oscillator strength. What is the sigma RMS, that is root mean square value. Root mean square is deviation of the how much difference between the F calculated and F experimental values. The quality of the parameter fit is generally described in terms of the root mean square RMS deviation, that is sigma RMS given by, that is a formula summation I 1 to n. So number of levels. So EI to experimental value, EI calculated value whole square divided by n. So here EI experimental and EI calculated are the experimental and calculated energy levels. So experimental and calculated energy levels respectively for the level I. And n is denotes, this n is denotes the total number of levels including in the energy level fit. So we are using this energy level fit. At that time, how many energy levels we are using, that is n value. Total number of energy levels by using fitting this F experimental and F calculated values. This is one program is there. By using that program only, we can calculate the sigma RMS value to difference between the F calculated and F experimental value. By using that value, we are getting the sigma RMS value. Root mean square deviation of the F experimental and the oscillator strength of the F experimental and F calculated values. By using this fit, we are calculating the sigma RMS value. That is sigma RMS value should be less than 1. Then only that fit will be optimized, well fitted equation. We are getting the sigma RMS value less than 1. That means 0.2 or 0.9 up to that in between. That is suppose 0.1 to 0.9 in between only. If less than should be unit. That means 1. So then only that fitting value will be, error will be very less. If crossing more than 1 means that error, that fitting is the level included in the energy levels fit will be not fitted well. That means we need to recheck all the values, and we have to calculate the again, and you have to check the RMS value should be less than 1. Then only your fitting will be well resolved peaks we are observing, and at the same time you are getting the good values of the Judd Ofelt intensity parameters. At the same time, F experimental, F calculated. Error should be very less. We have to minimize the error. So whenever you are getting, if 0.1 you are getting means that sigma RMS value that is completely well, all the observation peaks is well fitted with Judd Ofelt intensity parameters. That is fitting is very important in the calculation of the Judd Ofelt intensity parameters. Next, coming to the, by using that formulas only, we are calculated the Judd Ofelt intensity parameters of the erbium 3 plus doped silico-borate glasses, that is BS, GD, CA, erbium 0.5 glass. So these are the energy levels. So we are ground state, quaternion 15/2, different excited state. In this, in absorption peak, we are getting the 9 absorption curves, but in our 9 absorption, well resolved absorption peaks only are considering here only 6, 1, 2, 3, 4, 5, 6. So 6 absorption peaks we are used to fit the Judd Ofelt intensity parameters, that each and every peak energy value is low energy to higher energy. So by using these 6 absorption peaks, we are calculating the oscillator strength, F experimental and F calculated by using the above two formulas. Here in this fit, we are getting the sigma RMS value is very less, 0.034 into 10 power of minus 6. By using the 6 levels only, 6 energy levels of the excited state level from ground state to different excited state, we are considering only 6 among the 9 energy absorption peaks. We are considering only 6 well resolved absorption peaks only. By using 6 peaks and 6 energies corresponding values, we are calculating the F experimental and F calculated. By using this F experimental F calculated, we are getting the omega 2, omega 4, omega 6 parameters. This omega 2 is 3.16 into 10 power minus 20 centimeter square. Omega 4 is 1.32 into 10 power minus 20 centimeter square. Omega 6 is 0.99 into 10 power minus 20 centimeter square. The magnitude of the 3 JO intensity parameters were evaluated by using the JO theory, and evaluated JO parameters in the present work is shows the increasing order, that is omega 2 is greater than 2 omega 4 and omega 6. That is shows the larger value of omega T parameter in the erbium doped BSGD glass indicates the higher degree of covalence between the erbium 3 plus ions to argon ligands of the each and every erbium 3 plus ion is mainly interexchange to the ligand ions, that is O2 minus. So this is covalence between a higher degree covalence between the erbium 3 plus ions and surrounding environment of the oxygen ions, the O2 minus ions. This is shows the higher value of omega 2 value. In the present work, we are getting the omega 2 value. Omega 2 value is more compared to omega 4 and omega 2. That is why it indicates that the higher degree of covalence between the erbium 3 plus ions and oxygen 2 minus ions. This is the shows the Judd Ofelt intensity parameters we are calculating by using the JO theory. Next, we are going to discuss about the radiative properties. So, radiative properties such as radiative transition probability A and radiative lifetime tau R, and beta R is the branching ratios, and stimulated emission cross section is sigma lambda T. First, we are calculating the radiative transition probability AR value. The JO parameter along the refractive index. By using this calculation of the radiative transition probability, we need to substitute the refractive index value, N value. N value of the erbium 3 plus ions is around 1.632. This refractive index of the silicoborate glasses, particularly in erbium 3 plus ions, the N value is refractive index value is 1.632. So we are substituting JO parameters with refractive index are used to predict the radiative properties. This radiative transition property AR for the transition from ground state psi j to excited state psi dash j dash be calculated from the following equation. So by using this formula, so AR ground state psi j to psi j dash. This is from radiation transition probability ground state to excited state by using formula 64 pi 4 mu cube by 3h 2j plus 1 n into n square plus 2 whole square by 9 SED and SMED. SED electrical dipole and magnetic dipole. This electric dipole strength, magnetic dipole. This electric dipole and magnetic dipole is well resolved absorption peaks. There is a highly populated, that means highly effective transitions. Highly effective transition you can say is the MD. And that will be the magnetic dipole transition and electric dipole transition, lower effective transitions. These are the very important transitions from the absorption spectra. Absorption spectra we are calculating the SED and SMED, electrical dipole transition strength and magnetic dipole transition strength. By using this two SED and MED, N is the refractive index, J is the total angular momentum, and pi is the constant 3.14, mu is the energy value. By substituting these values, we are getting the radiative transition probability. By using this formula, we are calculating the radiative transition probability as the first one, AR value. Now we are going to calculate the V value is a radiative lifetime. So by using the radiative properties only, so radiative lifetime by JO theory, by using the Judd Ofelt intensity parameter, that is we are used to omega 2, omega 4 and omega 6 values at the same time with N value. N equal 1.63. Particularly in this case, we are getting N value is 1.62. By using omega 2, omega 4, omega 6 values, we are calculated here. By using this value and we are substituting refractive index value 1.62. By using these two values, we are getting the radiative transition probability. By getting transition probability, we are calculating the radiative lifetime. Tau R psi j equal 1 by 80 of psi j. This is total angular momentum. This is a radiative. Here the radiative transition probability. This is a total radiative transition probability. By 1 by total radiative transition probability, we are getting the radiative lifetime. These strong emission probabilities and more transition from the level lead to the faster decay and shorter lifetimes. That is tau R calculated from the JO parameters by using the lambda value can be compared with the experimental lifetimes tau experimental. We need to calculate the calculated value. The experimental value we are calculating by using the lifetime measurements. We can calculate the experimental value. In tau radiative, by using the JO theory, we are calculating the tau radiative lifetime. But comparing tau radiative and tau experimental values, the discrepancy between the tau or tau experimental can be attributed to non-radiative relaxation. That is mainly due to the multi-photon decay or energy transfer parameter. This is attributed to the non-radiative transition probability mainly takes place by using the due to the mainly multi-photon decay or energy transfer parameters. This is mainly involved to discrepancy of the non-radiative transition probability. This is mainly corresponds to the tau radiative lifetime and tau experimental lifetime. So by using this one, we are going to calculate the radiative lifetime. Next, C is the branching ratios. See, branching ratios BR is corresponding to the emission from the excited state and the psi dash j dash. This is we are getting this branching ratios we are calculating from the emission spectra, not in absorption spectra. By using emission spectra, by using emission spectra of erbium 3 plus ion. By using emission spectra of erbium 3 plus ion, we are calculating the branching ratios. This branching ratio beta are corresponding to the emission from an excited state level to its lower level of psi j, that is the excited state to ground state. We are getting from the emission spectra. By using emission spectra only, we are calculating the branching ratio value psi j and psi dash j dash. This IARE value, radiative transition property, total radiative transition property. This we are calculating from theoretically. In JO intensity parameters, we are calculating theoretically branching ratio value. The experimental branching ratio you need to calculate by using of emission spectra. In this one, beta experimental. So, branching ratio of experimental value we are calculating from the emission spectrum. This beta or radiative branching ratio we are getting from the JO theory. From JO we are comparing both beta experimental and beta radiative. We are calculating beta R from the JO theory. Beta experimental we are calculating from the emission spectra by using the each and every emission under the observation emission peak. We are taking the area and the emission wavelength corresponding that one. We are calculating the branching ratio by substituting in the Judd Ofelt intensity parameters. See, the branching ratio beta R can be used to predict the relative intensity of all emission lines originating from an excited state level to ground state. The experimental beta R can be found from the relative areas of the emission bands. So each and every emission bands relative areas we are taking, and we are taking that one, we have to calculate the experimental branching ratios, and we are comparing the radiative branching ratio and experimental branching ratios. This is almost both are similar. Equally we have to get the by using the JO theory. So error should be very less compared to theoretical model we are using. This last one is the peak stimulated emission cross section. So this is the one of the radiative properties. There is a peak stimulated emission section is the very important parameter in the laser glass spectroscopy. The peak stimulated emission cross section is sigma lambda p psi j. That means ground state to excited state between the states of psi j ground state to having the excited state of the IARE value can be expressed as. So here sigma cross section, that is emission cross section, calculating by using the lambda p, that means emission wavelength lambda p for 8 pi cn square. C is the, we are like n is the refractive index, delta effective wavelength is full width of image, that is delta effective wavelength, that means full width of image. You are calculating the by using the each and every emission peak and IARE value related to transition probability value. By using this value and full width of image and each and every peak energy value, wavelength value. This is where sigma lambda p is the transition peak of the wavelength. Delta effective is the effective bandwidth found by the dividing the area of the emission band by its average height. That is a full width of medium that is equal to delta effective. Next, good laser transition are characterized by the large cross section for the stimulated emission. So each and every glass, which glass having the higher value of the cross section, stimulated emission cross section value, that is highly useful for the good laser application. So this is one of the important and unique parameter for the laser glass spectroscopy. So the peak stimulated emission cross section is a very important parameter to calculate the laser action. At that time, you have to calculate important parameter is stimulated emission cross section. This stimulated emission cross section, by using this formula, we need calculated. Here, by calculating the stimulated emission cross section, we need emission wavelength lambda p and transition probability IARE value and effective wavelength, that is effective bandwidth, that is the delta effective. These three values substituting in this formula, we are calculating the stimulated emission cross section. Whenever this value are getting more, that is highly useful for the good laser applications. This is one of the important parameter in the laser glass spectroscopy. So these are the important properties of the Judd Ofelt intensity parameters and the radiative properties. Next, references. So these are the references recited in the present work. So this reference and this reference. V.R. Judo and in 1962 and J.S. Ofelt is Journal of Chemical Physics in 1962. These both papers used to calculate the Judd Ofelt intensity parameters. By using the kernel paper, you are taking this paper used to calculate the unit matrix, that is U2 value, U4 value, U6 values. Using this paper, we are substituting that values corresponding each and every wavelength and calculated the Judd Ofelt intensity parameters. This I presented paper omega 2 omega 4 emission values is published in this paper, Journal of Allies and Compounds in 2016. So these are the cited reference in the present work of the theoretical analysis for the Judd Ofelt JO intensity parameters. Thank you. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.